Hello my dear students, welcome to my YouTube channel that's Concepts of Chemistry. Before starting today's lecture, please do subscribe my channel. My dear students, today's topic for the lecture is sp3d2 hybridization with one lone pair and one pi bond in the structure. And for this concept, I'm taking the example of xenon oxyfluoride. So today we are going to do xenon oxyfluoride, that is XeOF4. So before coming to the hybridization, let's make the Lewis structure of XeOF4. So that's my Xe over here, the first fluorine, second fluorine, third fluorine, fourth fluorine, and the oxygen over here. Now let's talk about xenon first. Xenon, as we all know, xenon is the member of group number 18, so it's gonna have 8 electrons in its valence shell. So xenon is going to have 8 electrons in its valence shell because xenon is the member of group number 18 and it's a noble gas. So that's the first electron, second, third, fourth, fifth, sixth, seventh, and the eighth. Now let's talk about the fluorine. Fluorine, what's the atomic number of fluorine? That's 9. So the configuration will be 2, 7. That means fluorine is having 7 electrons in its valence shell. So let's mark 7 electrons around all the fluorine atoms. So I'm coming to the first fluorine, the first electron, second, third, fourth, fifth, sixth, and the seventh. Now let's come to the second fluorine. First electron, second, third, fourth, fifth, sixth, and the seventh. Now that's the third fluorine. First electron, second, third, fourth, fifth, sixth, and the seventh. Now let's come to the fourth fluorine. The first electron, second, third, fourth, fifth, sixth, and the seventh. Now let's talk about the oxygen atom. The atomic number of oxygen is 8. So its configuration will be 2, 6. That means oxygen is going to have 6 electrons in its valence shell. So let's mark 6 electrons around the oxygen atom. That's the first electron, second, third, fourth, fifth, and the sixth. Now what's gonna happen? First of all the fluorine atoms will have 1 bond with the xenon. So I'm marking the first bond of first fluorine with the xenon. That's the second bond of second fluorine with the xenon. That's the third bond of third fluorine with the xenon. And that's the fourth bond of fourth fluorine with the xenon. Now oxygen. The oxygen will make 2 bonds with the xenon. So that's the first bond and that's the second bond. Now let's count the number of electrons for all the fluorines and the oxygen after making bonds with the xenon. Let's come to the first fluorine. I'm counting the number of valence electrons for the first fluorine. That's the first electron, second, third, fourth, fifth, sixth, seventh, and the eighth. So the first fluorine has attained octet after the formation of 1 bond with the xenon. Now let's come to the second fluorine. I'm counting the electrons. 1, 2, 3, 4, 5, 6, 7, and the 8. So the second fluorine has also attained octet, that is 8 electrons after the formation of 1 bond with xenon. Now let's come to the third fluorine. That's the first electron, second, third, fourth, fifth, sixth, seventh, and the eighth. So the third fluorine has also attained octet, that is 8 electrons after the formation of 1 bond with xenon. Now let's come to the fourth fluorine. That's the first electron, second, third, fourth, fifth, sixth, seventh, and the eighth. So the fourth fluorine has also attained octet after the formation of 1 bond with xenon. Now, let's count the number of valence electron for the oxygen atom after the formation of two bonds with xenon. So that's the first electron, second, third, fourth, fifth, sixth, seventh, and the eighth. So the oxygen atom has also attained octet, that is 8 electrons, after forming two bonds with the xenon. Now, let's talk about xenon now. I am counting the number of valence electron for xenon after the formation of 1,1 bond with 4 fluorine atoms and 2 bonds with 1 oxygen atom. So that's the first electron, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th, 12th, 13th, and 14th. That means xenon has attained 14 electrons in its valence shell after the formation of 1,1 bond with 4 fluorine atoms and 2 bonds with 1 oxygen atom. Now, why so? Why xenon is achieving 14 electrons, that is more than 8, that is expansion of octet. Why there's the expansion of octet? Why xenon is achieving more than 8 electrons in its valence shell? Because xenon is having vacant d orbital in its valence shell. Now, let's talk about the hybridization. You are going to have this answer in the hybridization process. Now let's talk about the hybridization. Here, xenon is the central atom. Why so? Because xenon is forming maximum number of bonds. So as we all know, xenon is the member of group number 18. Now let's mark the group number 18. It starts from helium, neon, argon, krypton, xenon, radon, and the oganesson. Now, that's the period number 1, period number 2, 3, 4, 5, 6, and the 7. That means xenon belongs to the period number 5. Now, what's the general electronic configuration of group number 18? That's ns2, np, 6, where n is the period number. That means the electronic configuration of xenon will be 5s2, 5p6. So we got the valence electronic configuration of xenon that came out to be 5s2, 5p6. Now, xenon, the electronic configuration is 5s2, 5p6. Along with that, in the fifth shell, xenon is also having 5d subshell with 0 electrons, that is vacant d orbitals in the valence shell. Now let's make the orbital diagram for the electronic configuration. Now, as we all know, the s subshell has only one orbital. So I am making one box for the one orbital in case of 5s. Now, the p subshell always have 3 degenerate orbitals. What are degenerate orbitals? The orbitals that have equal energies. So that means 5p is having 3 degenerate orbitals. Now let's talk about the 5d. In case of 5d subshell, we have total of 5 degenerate orbitals. The orbitals with equal energies. So in 5d we are having total of 5 degenerate orbitals. So now, let's fill the electrons in all the orbitals according to the electronic configuration of xenon. Here the 5s is having, here 5s is having 2 electrons. So I am filling 2 electrons in s orbital. So that's the first electron with a spin of plus 1 by 2, and that's the second electron with a spin of minus 1 by 2. Now the 5p is having total of 6 electrons. So we have to fill 6 electrons in degenerate orbitals of 5p according to the Hund's rule. Hounsel states that in case of degenerate orbitals, firstly all the orbitals will get 1 electron each with a spin of plus 1 by 2. After that, pairing will start with a spin of minus 1 by 2. So I'm filling the electrons in 5p. That's the first electron in first orbital with a spin of plus 1 by 2. That's the second electron with a spin of plus 1 by 2, and that's the third electron with a spin of plus 1 by 2. So we got the 1 electron each in all the degenerate orbitals. Now the pairing will start from the fourth electron with a spin of minus 1 by 2. So we got the fourth electron in the first orbital with the spin of minus 1 by 2, the fifth orbital with a spin of minus 1 by 2, and the sixth electron with a spin of minus 1 by 2. So we got the 6 electrons in 5p and 2 electrons in 5s. Now let's come to the Lewis structure of the XeOF4. Here what we can see? We can easily see that xenon is forming total of 6 covalent bonds. 6 covalent bonds. Whenever there is a formation of one bond, then that bond is sigma. So there's the single bonds between all the fluorine atoms with the xenon. So the first bond of fluorine with the xenon is a sigma bond because it's a single bond. The another one is also sigma. The third one is also sigma. The fourth one is also sigma. So we got total of right now 4 sigma bonds. Now let's count the bonds of oxygen. The oxygen is forming 2 bonds with xenon. That means that's a double bond. In case of double bond, we always have the 1 sigma bond and the 1 pi bond. I'm repeating it again. Whenever there is a formation of 2 bonds between the 2 atoms, then out of that 2 bonds, the one bond is always sigma and another one is always pi. So that means here in total, we are having 5 sigma bonds and the 1 pi bond. But in total, firstly, we are having total of 6 covalent bonds. If xenon has to form 6 covalent bonds, then xenon atom must have 6 atomic orbitals containing 1 electron each that can overlap with the 4 atomic orbitals of 4 fluorine and the 2 oxygen atoms of 2 orbitals of 1 oxygen for the formation of 6 covalent bonds. I'm repeating it again. If xenon has to form total of 6 covalent bonds, then xenon must have 6 atomic orbitals containing 1 electron each that can overlap with the 4 atomic orbitals of 4 fluorine atoms and the 2 atomic orbitals of 1 oxygen atom for the formation of 6 covalent bonds. So, for that thing, we need to excite some electrons from 5p to 5d. How much electron we will excite? We will excite total of 3 electrons to get the 6 unpaired electrons in different 6 atomic orbitals. So that means here we need to excite the 1 electron from the 5p to the 5d. Now we have to excite the second electron from 5p to the 5d, and we have to excite this third electron from 5p to the 5d. By this way, we can have the 6 unpaired electrons or 1 electrons in 6 different atomic orbitals. So, first of all, this is called the ground state. Now let's make the excited state. That's the 5s. That's the 5p, and these are the 5 orbitals of 5d. Now the 5s is having 2 electrons. After the excitation, 5p is having total of 3 electrons, and after excitation, now 5d is acquiring 3 electrons from the 5p. So here we got the 6 atomic orbitals containing 1 electron each in case of xenon atom that can overlap with the 4 atomic orbitals of 4 fluorine atoms and the 2 atomic orbitals of 1 oxygen atom for the formation of 6 covalent bonds. So that's our excited state. Now let's come over here again. Now here we are having total of 5 sigma bonds and the 1 pi bond. So from this step hybridization will start. And in hybridization, only those orbitals will be involved which are having lone pair of electrons, and the another orbitals which are having one electron will form only sigma bonds, not the pi bonds. So in the Lewis structure, we are having 5 sigma bonds. So in hybridization process, I will be taking 5 atomic orbitals that are having one electron, and the one orbital from 5s which is having 2 electrons, that will be considered as the lone pair of electrons. So one atomic orbital from the 5s having the 2 electrons, and the 5 atomic orbitals, the 3 from the 5p and 2 from the 5d, so that I can have the 5 atomic orbitals having one electron which can form the 5 sigma bonds. So I got the 1s, 3p and 2d orbitals in intermixing process. So these 6 orbitals will intermix. The intermixing of atomic orbitals is called hybridization. So here total of 6 atomic orbitals are mixing. Accordingly that we are going to have 6 new hybrid orbitals. We are going to have 6 new hybrid orbitals with equal energies. That means that 6 new hybrid orbitals are also degenerate orbitals. So I am making 6 new hybrid orbitals. So I got these 6 new hybrid orbitals. So what will be the names of these hybrid orbitals? There is a mixing of, intermixing of 1s, 3p and 2d atomic orbitals. So the new hybrid orbital that has been formed will be termed as sp3d2 hybrid orbital. The second one is also sp3d2 hybrid orbital. Third one is also sp3d2 hybrid orbital. Fourth one is also sp3d2 hybrid orbital. Fifth one is also sp3d2 hybrid orbital, and sixth one is also sp3d2 hybrid orbital, which are having 16.66% S character, 50% P character and 33.32% D character per hybrid orbital. Now let's talk about the redistribution of electrons. How many electrons we have to redistribute in the hybrid orbitals? We were having the 2 electrons in 5s, the 3 in the 5p and a 2 in the 5d. So we got total of 7 electrons that has to be redistributed in the hybrid orbitals. So that's the first electron, second electron, third, fourth, fifth, sixth and the seventh. On the another hand, we are having these 3 unhybridized orbital, out of which one orbital is having electron. So let's make that also. We are left with now 3 unhybridized orbital from 5d, and these are the unhybridized orbitals. Out of that, one unhybridized orbital is having 1 electron. Now, whenever any hybrid orbital has 2 electrons, then that 2 electrons are termed as lone pair of electrons. That's lone pair of electrons. Let's come back to the Lewis structure. In the Lewis structure, we are having this to be the lone pair of electron which is present in one of the sp3d2 hybrid orbital. Now, let's come over here. Let's talk about the fluorine atom first. Fluorine, the atomic number is 9. So the valence electronic configuration in terms of shells and orbitals is, subshells and orbitals is 2s2, 2p, 5. So let's make the 2p orbital which is having 3 degenerate orbitals. The 2p subshell which is having 3 degenerate orbitals. Now it's having 5 electrons, the 1, the 2, the 3, the 4 and the 5th. So here we are left with one atomic orbital which is having 1 electron, and that atomic orbital will be going to overlap. So let's talk about the bonds. First of all, I'm making that's the 2p of first fluorine. 2p of first fluorine atom. The 2p is having 5 electrons. That's 1, that's 2, that's 3, that's 4 and that's 5. Now, we are left with one atomic orbital in fluorine which is going to have head-on overlap with the hybrid orbital sp3d2 of xenon. So, for the formation of sigma bond, we got the sigma bond to be sp3d2p. Why so? Because this sigma bond has been formed by head-on overlap of sp3d2 hybrid orbital of xenon with the p orbital of the first fluorine. Now, let's talk about the second fluorine now. That's the 2p of second fluorine atom. That's again having 5 electrons. That's 1, that's 2, that's 3, that's 4 and that's 5. Here again we are having one atomic orbital which is having 1 electron, and that's going to have head-on overlapping with the sp3d2 hybrid orbital of xenon for the formation of sigma bond. So we got the sigma bond to be sigma sp3d2p, because again this sigma bond has been formed by head-on overlap of sp3d2 hybrid orbital of xenon with the p orbital of fluorine. Now let's talk about the third fluorine atom. That's the 2p of third fluorine, and that's again having 5 electrons. That's 1, that's 2, that's 3, that's 4 and that's 5. Here also we are having one atomic orbital which is having 1 electron. That's going to have head-on overlap with the sp3d2 hybrid orbital of xenon for the formation of sigma bond. So we got this sigma bond to be sigma sp3d2p type. Now let's talk about the fourth fluorine. That's the 2p of fourth fluorine atom which is having 5 electrons. That's 1, that's 2, that's 3, that's 4, that's 5. Here also we are left with one atomic orbital which is having 1 electron, which is going to have head-on overlap with the one of the sp3d2 hybrid orbital of xenon for the formation of sigma bond, and that's again sigma sp3d2p. At last, let's talk about the oxygen atom. Let me take some different color. Now let's talk about the oxygen atom. Oxygen. What's the atomic number of oxygen? That's 8. So its valence electronic configuration will be 2s2p 4. So that means that's the 2p of oxygen which is having 4 electrons. So that's the first electron, second, third and the fourth. Here we are having two atomic orbitals which are having one electron. So one of the atomic orbital of oxygen is going to have head-on overlap with the sp3d2 hybrid orbital of the xenon for the formation of sigma bond, and that sigma bond again sp3d2 p type, because this sigma bond has been formed by head-on overlap of sp3d2 hybrid orbital of xenon with the p orbital of oxygen. Now we are having another atomic orbital which is having one electron, and this atomic orbital is going to have sidewise or lateral overlap with one of the unhybridized d orbital of xenon which is having one electron. So we got this to be the pi bond because this has been formed by sidewise or lateral overlapping of p orbital of oxygen with the unhybridized d orbital of xenon which is having one electron. So we got this pi bond to be of type p pi d pi, because here lateral overlapping is between the p orbital of oxygen and the d orbital of xenon. And in the previous lecture, I have already told you that hybrid orbitals never form pi bonds. That's why I haven't taken one orbital of 5D which is having one electron in the hybridization process, because that atomic orbital has to form the pi bonds and hybrid orbitals does not form the pi bonds. Now let's talk about the geometry of xenon oxyfluoride. We are having XeOF4. Was the hybridization of XeF4, that's sp3d2, was the standard structure of sp3d2 hybridization, that's octahedral. Now octahedral, here central atom is xenon, that's the first sigma bond with the fluorine atom, that's the second sigma bond with the fluorine atom, that's the third sigma bond with the fluorine atom, that's the fourth sigma bond with the fluorine atom. All the sigma bonds are of the type sigma sp3d2p, because all the sigma bonds have been formed by head-on overlap of sp3d2 hybrid orbital of xenon with the p orbitals of the fluorine. Now I am just imaginary linking the fluorine atoms. These are not the bonds. It is just a method to make you all understand this structure in 3 dimensions. Now let's talk about the oxygen. Oxygen is forming one sigma bond with xenon and one pi bond with xenon. And here also the sigma bond is sigma sp3d2p. So here we are having total of 5 sigma bonds, the 1, the 2, the 3, the 4 and the 5, and all the 5 sigma bonds are of type sigma sp3d2p. And we are having the pi bond between the xenon and oxygen which is of the type p pi d pi, because this pi bond has been formed by lateral overlapping of p orbital of oxygen with the d orbital of xenon. Now at last we are left with the lone pair which is present in one of the sp3d2 hybrid orbital. So let's make its arrangement in the structure. The lone pair is going to occupy one of the axial positions in the structure. So while naming the structure we have to ignore the lone pair. While naming the structure, we actually in general does not consider the lone pair. So this structure will be termed as square pyramidal, not the octahedral. So the name of this structure will be square pyramidal. So that's all about the hybridization of XeOF4, which is of the type sp3d2 containing 5 sigma bonds and 1 pi bond and 1 lone pair, and this will be termed as square pyramidal, not the octahedral. Now at last let's talk about the energy points, which I usually discuss in the last. Now, the energy is required to excite the electrons from 5p to 5d. So this process where electrons are exciting from 5p to 5d, sorry. So here's the process where electrons are exciting from 5p to 5d, and that's the endothermic process, and the name of that process is the promotional energy. So at this point, consumption here's the consumption of promotional energy. Now, second endothermic process is the intermixing of atomic orbitals that requires energy. Intermixing of atomic orbitals is called hybridization. So that energy will be called as hybridization energy. So here I am writing, here's the consumption of hybridization energy. Now, here we are having two endothermic processes, and at last we are having one exothermic process, that is energy is released during the formation of new sigma bonds and the pi bonds, which compensates the promotional energy and the hybridization energy. So I am writing, the energy is released, the energy is released during the formation of new sigma and pi bonds, which compensates the promotional energy and hybridization energy. As both the endothermic processes, promotional energy and hybridization energy gets compensated during the formation of new sigma and pi bonds between the hybrid orbitals of xenon and the p orbitals of 4 fluorine and the 1 oxygen atoms. That's why the formation of xenon oxyflouride XeOF4 is chemically feasible. So that's all for today. I hope you all understood today's lecture. If any student wants to book a paid one-to-one online online class to clear their doubts, then she can contact me. My phone number is mentioned on thumbnail of this lecture. Please do like, subscribe and share this channel to maximum number of students. Don't forget to press the subscribe button. Stay blessed.